good. Class recording has started. 12th period. How's it going? Hope it's, I hope, whatever. All right. So in case you have not done so already, 2 outlines for today. The one says heat, temperature, and thermal energy. 12th period, you guys finished that one yesterday, but we're going to review a little bit. And then one says heat transfer and thermodynamics. That's a new one. It's on the blue tray. Get us started first. Calendar. Where are we here? Sorry, 12th period, you don't get to zoom in, but yesterday, on Thursday, we did heat, temperature, heat, and thermal energy. We got through most of that. I actually recorded 12th period, so if you have to go back and watch it, it's there for you. Quiz as well. Quizzes you guys picked up at the beginning of class. 12th period, if you haven't yet, they're over in the tray. So today, heat transfer. So we talk about this idea of how we get this energy to move from one place to another. Conduction, convection, radiation. Some of those words you might have heard of. Some of those you might have not heard of. It's a good practical application day, so you'll notice that on your outline that I gave you today, there's a couple more of those questions that I want you to answer to try and explain some of these things that we see out there in the real world and why they happen. Fast forwarding to next week, Monday, calorimetry. So we'll talk about some how much energy is moving around during these processes of heat transfer. Monday is more of a math day, so we'll do a couple calculations, work through some of that stuff. Yep. Tuesday, we have a day to wrap things up, ask some questions, do some review stuff for upcoming tests. Then block day, next lab, specific heat of an unknown metal. That goes along with the last part of this unit on the heat and heat transfer and stuff like that. And then we are scheduled for tests on Friday, next Friday, 1 week from today. Objective sheet is posted already, so if you haven't got yourself a copy of that, it might be a good idea to start looking at some of those things. It is kind of a long chapter. I would not say it is the hardest chapter we do all year. It's actually probably one of the easier ones, a lot of definitions and stuff, but it is kind of long, so it might be a good idea to start looking at those things sooner rather than later. Questions? Lab reports are getting there. I should have them done by the end of the weekend, so hopefully Sunday you'll see a score show up as far as lab reports go. All right. Oh, also, I think I mentioned to you guys yesterday, the lauric acid cooling curve lab, the one that was supposed to be due yesterday, but I think we discussed that I'm not going to grade it probably until next week. Just don't forget about it if you haven't turned it in yet. So if you haven't turned that lab in yet, make sure you get it turned in sometime soon. Okay? All right. So with that being said, let's go here. So over the past couple of days, we introduced 3 terms that sort of sound familiar or sort of sound similar, but they are all different. And those terms were heat, temperature, and thermal energy. I want you to take 1 minute, and I want you to discuss with the people around you in small groups what are the differences between those 3 terms: heat, temperature, and thermal energy. Discuss. Go.
Jason, this is for science.
No.
So it's like, I'll take the temperature.
Yeah, I get it. How much?
Energy is the ability to do damage.
They just keep jumping.
Thermal energy is the total amount of energy.
Thermal energy.
All right, so let's discuss. So, first, let's talk about temperature. What does the temperature tell you? Temperature of a substance tells you what?
The average kinetic energy.
The average kinetic energy of the particles, which means basically it's telling you about the what? Their motion. Okay? What about heats? What does heat tell you? Kraft, go ahead.
It
the transfer of thermal energy from one object to another.
Transfer of thermal energy from one object to another. We're going to spend most of the period today talking about heat and how that gets done. How do we transfer thermal energy from one object to another? Okay. And then the last one, thermal energy. Okay. Emily, go ahead.
The total amount of motion of the particle.
Total amount of motion. So we said now when we talk about thermal energy, we have to take into account a couple of things, right?
Yeah.
What factors go into thermal energy?
Mass.
Mass, because it tells you how much stuff is there.
State of matter.
State of matter, because that tells you about like attractions and things like that.
Temperature.
And then temperature tells you about the motion. Okay? So those three things, they all sound kind of similar, but like it says up here on the title screen from yesterday, right? Know your definitions. Make sure you keep them straight. Okay? Towards the end of your class yesterday, we were talking about this bucket. Okay? Now, I misled you a little bit because what we were talking about in class was different than actually what your outline says. So don't write this down just yet, okay? We discussed yesterday that judging by this picture, what could you probably tell me about the temperature of these two things here? All right? Temperature based on this picture. Ben, go ahead.
That the teacup is warmer than the big bucket of water.
Teacup, higher temperature than big bucket of water. Ben, what does that mean if we say that the teacup has a higher temperature than the big bucket of water?
But there's more energy in the particles than the
Let's say there's more what in particles?
more thermal energy.
No. There's more kinetic energy or more motion. Those particles are moving faster. Okay? But, Ben, now jumping into that other word, right? Does that necessarily mean that there is more thermal energy in this teacup than there is in this bucket? Not necessarily, right? Because we just discussed there are a couple other factors that go into determining thermal energy. Is Emily ready to answer a question now, or is she too distracted? Okay. So, Emily, those factors that we discussed that determine how much thermal energy something has, what are they?
Mass, temperature, and state of matter.
Mass, temperature, and state of matter. So if we look here, right, what are we seeing, especially about the mass here, right? Bucket has way more mass, but we don't know exactly the difference in temperature, right? Okay. But on your outline, that's not what it says. Sorry, I should have pulled this up before. Stand by. Quietly, stand by. Yeah. On your outline, brother. Continue to quietly stand by. Yes, Rachel.
Please signifer right now.
How about the end of the recording? So, that's my polite way of saying no, because you're gonna forget about it by then. So,
I'll write it down.
I mean, you know. Hey, I just want you to know we're recording class right now. So, yeah, well, I just had to do this. Waiting for something to open. Fancy this going on. Sure. Oh, listen, high tech. We spend no expense here. Machines, coffee mugs. I don't know what that whiteboard cleaner. You got everything down here. Science department's where it's at.
Give me like a piece of chalk. Go to it. Can I see Emily Simon for a second?
So you know it's her birthday Sunday?
It is.
Yeah. Rachel really wants to sit in call.
12, 13?
15.
Running mailboxes full of
All right. 12th period's going to be really confused when they go. All right. According to your outline, it says even though the picture may not look like it, assume that the water in the bucket and water in the bucket and water in the cup have the same temperature. So if they have the same temperature, what does that mean? Beaver? They have the same amount of kinetic energy. I'll give you that. Okay. Meaning, what about their motion, Beaver? They're about the same. They're the same speed, right? So if the water in the bucket and the water in the cup have the same temperature, that means that their particles move the same speed. But now, can we make an assumption about thermal energy? Which one has more thermal energy? Done. we'll know if we can assume they have the same temperature. Okay? Because we said that thermal energy depends on three things, right? State of matter, temperature, and mass. If they have the same temperature and they have the same state of matter, mass is bigger here, so the bucket would have more thermal energy if we assume that they were the same temperature. Correct question, or are you good?
No, it's just like.
Sorry, I misled you guys yesterday. I forgot what your outline actually said. So. Yeah, judging by that picture, we couldn't make an assumption about thermal energy, but if we assume they are the same temperature, the bucket would definitely do more damage to you than the cup of coffee or tea or whatever it is. Okay. Good there? All right. Just to review this last point, two more questions on that outline. So you got a picture of a kid holding a sparkler. I know it looks kind of like a magic wand, but it's a sparkler. Okay. So, do the sparks have a high temperature or a low temperature? Sparks have a high temperature. Rachel, what does that mean if they have a high temperature?
It means that the motion is high.
They have a lot, the particles that make up those sparks have a lot of motion. They have a lot of kinetic energy. But, do the sparks have a lot of thermal energy? No. Why not? They're real small, right? So just from personal experience, okay, if you've ever held one of those sparkler things, right? Okay, if a spark gets on your hand, does it hurt? It hurts a little bit, right? But is it enough to, like, make your hand fall off?
Yeah.
Well, maybe like an M80 or something that, but
I use pretty epic sparklers.
my epic sparkler. Of course, I forgot to, rule out the possibility that it was an epic sparkler. So, high temperature, not a lot of thermal energy though. Yeah, I know. Not sure why I did that. All right, are we good there? All right, last topic here. It's pretty straightforward. Thermal expansion and contraction. Based on the motion of the particles, as the temperature changes, the volume will change as well. You've seen this before, all right? Generally, as things get hotter, what happens to them? They expand, right? So generally, higher temps come along with increased motion, and increased motion leads to a larger volume. Okay? So underneath your outline, right, those all just say increase, right? As temperature increases, motion of the particles increases, and that means volume increases. Whereas if temperature decreases, motion decreases, and the volume decreases. Generally. Not always the case, but generally. There's one pretty big exception, that being when water freezes, okay, which is kind of important to us here on Earth, but does sort of buck the trend as far as how matter behaves. But, just a couple of examples. Sorry. So, here is a picture that just represents the changes in volume and something going from a solid to a liquid to a gas, right? Here, this is kind of a bummer. You ever go out to dinner maybe when you were a little kid and you got yourself a balloon, right? But then you mistakenly left it in the car overnight because you were so excited when you got home or you fell asleep or something like that, and it's in the wintertime and it gets cold in the car, and you come back the next day, and what does your balloon look like? It's not as impressive as it was the evening before, right? Yeah, tired. Yeah, doesn't he just look sad? Although he doesn't look real happy in the summertime picture to begin with.
That's a guy, the first picture.
Yeah, totally. Definitely a guy. So.
He looks like a homeless person.
Well, I guess I shouldn't make that broad assumption. I don't know if it's really a guy.
I thought it was like a brother and sister maybe. Looks like
Ronnie, you don't know what I got.
maybe he was playing dress up.
Or
What I got.
things like this. Anybody have an old school thermostat in their house? The one that you actually have to like turn the dial and not like a digital one? Yeah? So, the thermostat works on the idea of thermal expansion and contraction. There is a little coil of wire, or not wire, it's a little coil of metal inside of your thermostat. And it's actually made out of two metals, brass and iron. And they expand and contract at different rates. So, in the wintertime, when it gets cold in your house, that coil will contract and get smaller. And as it gets smaller, when it gets small enough to a certain point, it flips a switch. Guess what that switch is attached to? The heater. And it turns the heater on. And then, when the heater's on and it gets warmer in your room, in the house, what starts happening to that little metal coil? It expands, and as it expands, guess what it does? Turn the switch off. Alright? And it works in the same way in summertime, right? If it gets too hot in the house, the little coil expands and turns the switch to the air conditioner on, and then as it cools down, it contracts and it turns the switch off. Alright? Ever see these things when you go across a bridge, maybe at like the park, if you're on like a walking bridge or something like that, okay? These are called expansion joints. In the summertime, what happens to this bridge?
It's hot.
It gets hot, and if it gets hot, what happens to its volume? Maybe not that hot, but it gets bigger. If you don't allow space for that bridge to get bigger, guess what it's going to do to itself? It's going to crack itself, right? So this expansion joint allows the bridge to actually get bigger in the summertime and cool down in the wintertime. Okay? Or it might end up like this. Come on, picture. Oh, there it is, right? So, in the summertime, when it gets real hot and it gets real dry, this mud that used to have a bunch of water in it, that mud dries out and it becomes a gas. And when it becomes a gas, what happens? Or sorry, not the mud. The water that's in the mud becomes a gas. But how much volume does that gas have compared to the liquid state? More volume. What's it start doing to the ground? Starts cracking it open, just like it would crack the bridge. Okay. Good there? Okay. Questions? All right. Let's talk about how this actually happens with thermal energy transfer and thermodynamics. So, the fact that this outline is called thermal energy transfer means we're going to be dealing with what word from our last outline? Heat, right? This is how heat occurs. This is how energy transfers from one place to another place. There are three ways that it can happen. So let's start with the first one that's on your outline. And that first one is called conduction. Okay? What? Oh my goodness, that's exactly the same as before, right? So we learned earlier that heat is what? The transfer of thermal energy from one object to another because of a temperature difference. Heat flows spontaneously from objects with high temperatures to objects with lower temperatures. So, first outline, right? First part of the outline. These are definitions from the last outline. Okay. Heat, transfer of thermal energy from one object to another because of a temperature difference. Heat flows spontaneously from objects with high temps to objects with low temps. Good there? Okay. How does it happen? First, conduction. defined as the transfer of thermal energy with no transfer of matter. So everything stays where it is, but we get the energy from one place to another. Conduction occurs within particles of a material or between objects that are touching. So let's go back to our analogy about states of matter that we discussed before of you guys in school. Okay? Let's say we have to transfer energy, the ability to cause change, from one part of the room to the other part of the room. Let's say in this case, playing the role of energy, the ability to cause change, is the classic what? Okay, I was thinking, no. How about like a note to somebody, right? You gotta pass them a note, right? It says, I don't know, do you like me? Check one. Yes, no. Call me, maybe. Yes, no. Right, okay. But we got to get that note from one side of the room to the other side of the room, because the object of your affection is way over there. Right? Ben playing the role of, yeah. So anyway, now, can we get the note from one side of the room to the other side of the room without anybody actually taking it there?
Yes.
Sure. What do? Every time I turn around and look at the board, it goes one step further, right? Except I know when these things happen. So, I know that, Brittany and Caitlin just sit back there and talk the whole period. Usually quietly, but sometimes not so much. But anyway, can we get that note across the room? Yes, we can get the note across the room. Does anybody have to take it there? No, nobody has to take it there. All right? That's conduction. We have transferred energy without transferring matter. Nobody moved, but that note got from one side of the room to the other side of the room. How fast does it happen?
Medium speed.
Kind of depends. Okay? Kind of depends on how close things are. Question on your outline. Question says, use pictures to the left to explain why conduction occurs more slowly in gases than it does in solids or liquids.
Because in gas, the particles are far apart and aren't really attracted to each other, so they won't want to pass on the energy.
Okay. Particles in a gas are real far apart, right? Imagine trying to pass a note to somebody in gym class, right? That probably would take a little while. Make sure that you got the right connection, you got it to the right person. That would probably take a while, right? But here in class, right, solid, everybody's real close together, that energy passes real quickly from one to the next. Conduction, energy transfer, happens much faster in solids than it does in gases, as long as that stuff is a good conductor. Okay? Let's say you're trying to pass a note in class, but you got a bunch of people that actually follow the rules and pay attention in class, and they don't want to pass notes from one person to the next. All right? Will the note passing happen quickly? No. But it's not because the particles aren't close together, it's just because those particles aren't passing the note. Okay? We refer to those things as insulators versus conductors. Okay? So, a conductor, right? A material that conducts thermal energy well. Right? This would be like your bad kids don't pay attention in school. They're more than happy to pass a note. Well, they'll probably read it first, but then pass it to the next person, right? Okay. Things like metal and floor tiles. Ooh, that's a bad one. Okay. So let's talk about floor tiles. And floor tiles being good conductors. Right? We ever have this unfortunate experience in the morning that you get up and you're kind of half asleep anyway, and you stumble to the bathroom, and you take one step into the bathroom, and what does it feel like?
Yeah.
Freezing, right? Is that because the floor in the bathroom is colder than the floor in the hallway? They've been in the same house all night, right? Is your body temperature different when you step from the hallway into the bathroom? No. So there is the same difference in temperature between your body and the floor. But the carpet seems nice, warm, and cozy, and the floor in the bathroom seems freezing. Why?
It's nice in the summer.
What?
It's nice in the
It's true. Right? Why? Because the floor, the tiles in the bathroom, or the linoleum, like if you're not in a fancy house like my house, right? That floor conducts heat a lot better than the carpet does. So which way does heat flow? From what to what? From hot to cold. You're hot, the floor is cold. Which way is heat flowing? Out of you and into the floor. What does that feel like to you?
Cold.
That feels cold. Why is the carpet a much worse conductor than the floor? Good question. Good.
It's very tough for particles to move through it.
Say again?
Because it's very tough for particles to move through it.
Yes, it's tough for particles to move through it for two reasons. One, it's made out of synthetic fibers, whatever, okay? But two, what does carpet look like compared to the tile floor? If I put a sample of tile and a sample of carpet right next to each other, what would you see? Especially if you looked at them from the side.
Oh, carpet's there.
Carpet's thicker, but is it really thicker? It is, but what is most of that thickness?
It's like carpet pieces sticking up.
Yeah, what's in between those carpet pieces though?
More carpet.
No.
Good match.
No. What's in between those carpet pieces? Air. And what is air made out of, state of matter-wise? Gas. Is gas a good conductor of heat? No. Why is your big puffy coat warmer for you in the wintertime? What's inside that big puffy coat? A bunch of air. Does it conduct heat away from your body into the cool air? No, it doesn't. There's a bunch of air there, right? Thermal insulators, material that conducts thermal energy poorly. Hold on a second. Thermal insulators are things that conduct energy poorly. Things like the wooden or plastic handle on a pan, air, foam cups, a wool sweater. Why are all those things bad conductors? Because they're big and poofy. And what does that big poofiness come from? There's a lot of air in there. And air is a bad conductor. Why does a polar pop, or whatever it is, what's that thing you get at Speedway?
Speedy freeze.
A speedy freeze, but the speedy freeze comes in what kind of a cup? A foam cup, right? What do they call it? They have a name. No, they call it like the cup something. What do they, I don't know. Whatever. Anyway, a styrofoam cup keeps hot things hot and cold things cold. Why? Because what does it not allow to happen? It doesn't allow heat transfer. Right? If you go to Starbucks, you go to Panera, you get your hot drink in a cup, right? But what do they put on the outside of that cup? That little cardboard sleeve, right? What's that cardboard sleeve made out of? Cardboard, but if you look at it, it's all like folded up like this, right? Why? Because what's in between all those folds? A bunch of air. So it doesn't conduct heat as well as like the actual cup itself. Does that make sense? Okay. So there are two terms on that sheet, or two lines in conductor and insulator that we haven't covered yet. Specific heat. We'll cover specific heat on Monday when we talk about calorimetry. But insulators usually have high specific heat values, whereas conductors have low specific heat values. You have no idea what that means yet, but that's okay. All right. Good on conduction. Okay? All right. Next, convection. Okay? Convection is the transfer of thermal energy when the particles of a fluid, either a liquid or a gas, move from one place to another. So if we go back to our analogy that we used earlier in the period, sorry, finish right. If we use our analogy from earlier in the period of quote unquote passing the notes, what would this be? What would convection be? Describe to me what convection would look like. Actually, here. Describe to each other what convection would look like if you're trying to pass a note.
That's right. Convection was just like,
Give me the whole way.
oh, no, that's pretty. What?
Grabbing a pencil, grabbing a pencil, missing the tab.
All right. Let's discuss. So, someone want to give me their example of what convection would look like in a real classroom? Joe, go ahead.
Someone gets up and gives the person a note.
Someone's being sly and they're like, oh, I have something to throw away. I need to walk over to the garbage can. Drop it on the desk on the way by, right? Did the energy get from one point to another?
Yes.
Yes, but something had to take it there, right? Someone gets up, walks across the room, drops the note off, hopefully more, being coy about it, as if pretending they're trying to throw something away or something like that, okay? And get it from there. Does that make sense? Okay. All right. With that being said, okay, places where you'll see convection. Anybody have a convection oven at their house? A convection oven is basically just what? It's an oven, but what does it have in it? Yeah, it has hot air, but all ovens have hot air. What makes a convection oven different? No, it has fans in it. What do those fans do? They just move the hot air around. Okay? What? I didn't even know. A lot of time, pizza ovens are convection ovens. How long does it take a pizza, or how long does it take a convection oven to cook a pizza? Not very long. A lot faster than your oven at home, and you don't have the air in it, right? Why does it work? Well, the oven fills up with hot air, right? Hot air gets next to the cold pizza. Which way does energy flow? In from the hot air into the cold pizza. Until what? Until they're the same temperature, right? If that's the case, does any more heat transfer happen? No. So what does the convection oven do? What does the fan do? No. No. The air that's around the pizza is cold now because it's lost its energy to the pizza. So what does the fan do? It blows that cold air away, and what does it replace it with? Nice warm air. And when that warm air loses heat to the pizza, what does it do? Blows that air away and replaces it with new hot air. Does that make sense? Okay. With that being said, let's take a look at your outline. And your outline down at the bottom says, this here is the idea of wind chill. Right? Why does it feel colder on a windy day? Because Brian Weatherman says so. Yes, that is true. Although Brian Weatherman is based in science. So I've never met Brian Weatherman before, but
I don't know if
I've seen that.
that's what I've heard. All right. Why does it feel colder on a windy day? Why do we have something called a wind chill? So besides these two, anybody? Hey, discuss. Go ahead. Discuss with each other. Why does wind chill work?
grapes, right?
Yeah, I could say 4.
All right.
I can't.
Do you want to try it out on me first before you? Okay.
So the gas, the air forms a giant fist and punches you in the face and says be cold. Wow.
That is a good analogy. Not a correct one, but a good one. All right. So, what did we come up with? Emily, you had your hand up. You were going to say it before I told you guys to talk in small groups.
I don't know, but
Tell me.
So it's because the cold air is moving.
Okay.
And since we're warmer, when it moves against us, it feels cold.
Okay. So, if there's cold air around you, right, your body temperature is about 98.6 degrees. The air outside today is 30. Which way is energy going to flow? Out of you and into that cold air, right? Okay? But now, what happens to that air that's around you? Somebody said it.
It's warm.
It gets warmer, right? If that's the case, if the air around you gets warmer, will you continue to lose heat? No. Because if the temperature's the same, you don't lose heat. But on a windy day, that air that's around you that's warmer now, what happens to it? Gets blown away and gets replaced with what?
Cold air.
More cold air, and you lose more heat. Alright? We will continue this discussion on Monday.
Cold period.
Hey, there is reading assignment and some questions dealing with heat transfer on the calendar. Check them out, please.